Okay, good evening. So we'll start this topic on magnetics for power electronics. So this is a chapter that was actually prepared by my colleague, Dr. Naga Brahmendra, who was with NUS, which is currently working at NTU. So I'll be just using his material. Now, magnetics actually refers to the various type of the inductors, the transformers, right? All that we have seen, right? For example, we know that in induct all the non-isolated DC-DC converters like buck, boost, etc. We use an inductor, right? We use inductor. Then we also use transformers in the isolated DC-DC converters, right? So this chapter is basically how to design those values. You have to literally build those values, because many times to get certain type of response, you need to fix certain values. So you cannot get those materials, those inductor transformers directly from the market, and you may have to do the winding yourselves, right? So that's how we learn, what exactly is the principle of operation of inductor transformers, which together are called magnetics. Then we'll do the modeling, equivalent circuit, and we can also calculate the losses in this, because if you want to calculate the efficiency of the converter that you design, then you should know the losses in different parts. Earlier, we have seen the losses in the switches, right? The switching loss and conduction loss. Then the other elements are the inductors, right? There is some loss in these inductors because, as you might be knowing, inductor is nothing but a coil. And this coil would definitely have some resistance, though it is supposed to have inductance, but because it's a wire, so it will always have some resistance, right? So this resistance would cause some loss in the inductor, right? So you should be able to estimate how much is the loss at the operating point, so that you can calculate whether our converter is having the required efficiency or not. Okay. Now, so like I said, magnetics for power electronics include inductors, which are just single inductors, which are, as I said, it's in buck converter, boost converter, or buck boost converter, right? So this, we already saw that pure inductors are used. Then we also see there are a couple inductors or transformers. Now, what is the difference? Maybe somebody can tell me. The coupled inductors basically has two coils. Transformer also has two coils, but the way they operate is slightly different. Coupled inductor, as you can see in flyback, so normally one coil conducts at the time, the other coil does not, right? But as a transformer, we have used transformer in forward converters. Partially, there's a transformer operation between winding one, primary and secondary, but primary and tertiary can be treated as a coupled inductor, right? So basically, there are multiple coils on the same core. So all these are called magnetics. So every power converter in the market as a product will have at least one magnetic component, right? You might have seen all the converters we learned, all of them require one magnetic component, because the magnetic components actually add as the filtering, right? Because when we do switching, the smoothing of the voltage and current is necessary. So we need filtering. So inductors, capacitors together do the filtering. So that's why this is a must in any power converter, right? And of course, if just inductor, they do filter, or energy storage. If in a coupled inductor, as you can see, one charges, then it supplies power to the secondary side, or galvanic isolation, right? When there is a transformer, there is galvanic isolation between the low voltage and high voltage. And the magnetic components influence the power conversion efficiency, power density, and bandwidth. So this is important concept, that efficiency, like I said, means you need to minimize the losses, and one possible lossy element is the inductor. So you have to design it properly so that the loss in the magnetic element is actually minimum. Similarly, the size of the inductor adds to the size of the converter, right? So if you have a large bulky inductor, then you can see that it actually takes substantial amount of volume of the overall converter. Third thing is the bandwidth of the converter. Bandwidth basically at what switching frequency they operate, right? So all these things decided by the magnetics. So you can see that the frequency, switching frequency and the size of the filtering elements are closely linked. In fact, generally speaking, if the frequency is higher, this leads to inductor capacitor size becoming lower, right? That's basically the principle. Okay, so what we'll do next is we'll do some basic revision of the magnetic circuit. So what is magnetic circuit? It's basically the overall circuit. When I call circuit, because we'll see later on that we'll try to study the magnetic circuit as an equivalent to the electrical circuit. We all know electrical circuit, right? Electrical circuit basically has a voltage source, and we have some loads which are normally could be resistive loads, right? If we have a DC circuit or even AC circuit. So we have voltage, there's a resistance, and then there is current. Depending upon AC or DC, so there will be current. You can see that I equals to Vs over R. So in a circuit, there is a source, then the resistance of the path of current flow, and those two together decide the current flow. Similarly, in the magnetic circuit is basically creation of the magnetic flux, right? So magnetic flux will be created by a source, and that source, then the amount of flux also will be related or can be related in a way similar to the electrical circuit. So we have some definitions here that in the electrical circuit or electrical conductor, if current is flowing, then we can define one more term here, which is called current density, right? So current divided by the cross-section area here will be divided, it's called the current density. Similarly, in a magnetic circuit where the flux is there, we can define a term called flux density. So we can see that flux and current are actually related, that the electrical current is related to magnetic flux in these two circuits. Okay, so you can see here, I think there's a typo here, it should be winding W. C is the core and W is the winding. Now, we'll see later on that the flux density inside a magnetic circuit depends upon many things. So, of course, we'll see that it depends upon the source, which is called magnetomotive force. We'll define magnetomotive force in the next slide. And this is similar to our voltage, which if you probably remember, voltage is known as electromotive force. So it's important for us to see the link between the two circuits. So as you know, the basic cause of magnetic flux production, or the main source, is actually a current flowing in a conductor. Whenever current flows in any conductor, basically charge when it is in motion, right? That's what is current. The charge when it is in motion produces a magnetic field around it, or magnetic flux in the neighborhood, right? So if you have current constantly flowing because of a circuit like this, there's a source, and then you have some coils, there will be some resistance, so there will be a current flowing in this coil. Now this current would produce magnetic flux around the conductor. right? So as you know, it's in fact the basic definition is that whenever current flows in any conductor, it will always produce the magnetic flux around it, right? So here we'll remember a couple of laws from physics, but the main idea first is that magnetomotive force is the external force that is required to set up the magnetic flux lines in a magnetic material, right? So whenever you want to produce a magnet or magnetic field, you need a source which is called the magnetomotive force. And what exactly is it? It is, you can see here, it is number of turns of the coil multiplied by the current in the coil. If it's a DC circuit, or you can say it is an AC, we write small letters. So the magnetomotive force is given by the number of turns multiplied by the current in the coil. It has a unit of ampere turns, AT, because it's number of turns and current. So that's why it is called ampere turns. And this is analogous to the voltage in electrical circuits, right? And then there is one more term we define, it's called magnetic field intensity. So these words are normally, somewhat similar sounding. Magnetic flux density, magnetic field intensity, right? So magnetic flux density we had defined earlier, which is defined as the flux per unit area. So these are the flux lines passing through or established inside a magnetic material, which is called the core. So the number of flux lines per unit area is called the magnetic flux density or flux density. So what is magnetic field intensity? It is defined as the measure of the force experienced by charged particle in the magnetic field. And this could be another definition, but there are one more definition is the magnetomotive force per unit length of the magnetic loop. Right, for unit length of the magnetic loop. So what is a magnetic loop? We can see here. The magnetic loop is basically the starting from any point here, the whole length in which flux is established. Flux lines are actually always closed lines, right? From beginning to the end, you can have like electrical circuit always flow in a closed circuit. So flux lines will always be having beginning and end, right? They'll be closed. So you can see the whole length of this line, flux line, it's called the magnetic. It's the length of the magnetic loop, right? That's the length of the magnetic loop. Now, what you assume here is that this MMF, which is the number of turns multiplied by the current produced or provided by the coil, is the cause of the magnetic flux in the core. So if you know the overall core length, or which is the length of the magnetic loop, then this cause, which is the magnetomotive force per unit length, the magnetomotive force per unit length is called the magnetic field intensity. So you can see that this is related to the two things. One, the number of the ampere turns. The second, the length of the magnetic path. So if it is related to the ampere turns and so this is the field intensity, the cause of the magnetic flux. So we'll see later on that if we increase this quantity either by increasing the number of turns or increasing the current, which is the numerator, or by decreasing the path of the magnetic loop, the length of the magnetic loop, then this factor, which is magnetic field intensity, will be higher. And later we will also see that there is one more definition or one more formula, that the flux density B is related to this magnetic field intensity, and it is in fact proportional with a proportionality constant of which is called permeability, right? So in fact, this is called the permeability of the material, magnetic permeability. Now here I just want to say what is the importance of this term here, permeability of the material. The core, whatever is the core made of, the material of the core would have this property called magnetic permeability. Now, as you can see, for the same magnetic field intensity, which is decided by the number of turns, the current, and the length of the core, the actual number of flux, the flux density, would depend upon the material, right? So this is similar to say that if you have any conductor and you connect it to a voltage source, the actual current will depend upon voltage source, length of the conductor, the size of the conductor, as well as the material of the conductor, right? Something similar happens here. So you can see that's basically the concept of permeability. We'll talk about that later again. Now, electromagnet, you might have known that basically there are current carrying conductors, they produce magnetic field around it. And so electromagnet is nothing but a magnet that is produced by the current through the coil. And then we have Ampere's law, which says that the net MMF around closed magnetic path is equal to the net current passing through the interior of the path. So what it means is that if you want to find out how much is the H, or the field intensity around it, you have to, Ampere's law basically says that it is, if you find any current conductor, carry conductor, or a single conductor or coil, number of coils, and you want to find what is the magnetic field intensity along a path in its neighborhood, then you can use Ampere's law, right? For a single conductor, it is easy to find. If you take a path which is at a distance r, a circular path, then the overall length will be 2 pi r, and h will be uniform because it depends upon the distance. So here you can see that the h will be equal to the current in the coil in the conductor divided by 2 pi r. So it depends upon the distance from the conductor. If you go close to the conductor, then the field intensity will be higher. If you go further away, it will be inversely proportional, right? Inversely reducing. Now, what it means is that if you have any current carrying conductor, there will always be this tendency to produce magnetic field in the neighborhood, right? So basically, if you have large conductors which carry, the power conductors which carry thousands of amperes, naturally there is strong magnetic field intensity near that, so that if you have any magnetic material, then there will be large magnetic field induced. But anyway, we can also use the same thing in the case of the electromagnet that we're talking about here. If that integration from Ampere's law, integration of H around the path, if you can assume that the H is uniform because of the way it is spread, the coils are spread. If it is uniform, it is shown like this, but the coil would be spread, uniformly around this. So if H would be constant, then the overall definition, you can see this integration will be coming as dl. H will be constant, integration of dl will be H times Lm. So this will be subscript, right? So overall length of the path. So in other words, your H, and that is equal to Ni ampere according to Ampere's law, because that is what is the number of turns multiplied by the current. So that gives basically the definition of Ni over Lm. So the magnetic field intensity. Okay, so that's the definition of magnetic field intensity. Now let me just pause here to see whether you guys are clear about what is magnetic field intensity, what is flux density, right? So these terms must be clear before we proceed. Okay, so we are learning about magnetic circuit. We learned about the source. We learned about the cause of the magnetic flux, the magnetic field intensity. The effect is the flux density. So I can say, normally I try to remember in terms of cause and effect, source and output. So cause is the MMF, magnetomotive force, which is given in terms of the magnetic field intensity. The cause is the flux, which is given in terms of the flux density, right? So now how do we really link, rather how to draw an equivalence between the magnetic circuit and the electric circuit? So here are the things. The flux is the result in a magnetic circuit. The current is the result in electrical circuit. Flux density is the flux per unit area. We can have something called current density, the current for unit area. You can see the unit. Now, magnetomotive force and electromotive force. Voltage is also known as electromotive force. So voltage is equivalent to MMF, which is MMF is nothing but Ni, which is given as ampere turns, and in electrical circuit is the source voltage. Magnetic field intensity, right? That's the strength of the magnetic field, which is the ampere turns per unit length. We can have electric field actually, which is defined as the voltage over M. So normally this is used in when there is voltage between 2 points and the distance between them, that's called electric field intensity. That's E, right? E equals to V over distance. We can draw some equivalent magnetic field strength or magnetic field intensity and electric field intensity, electric field. Okay, I think this is the term that we'll be seeing here. This is called reluctance and resistance. So we all know what is resistance. Resistance is Ohm's law, V over I. Now here on the in the magnetic circuit, we also represent it by I, R, like this, and that's the cause, which is MMF, or ampere turns actually, Ni over the effect. Effect is flux, right? So you can see that resistance and reluctance are also related. Okay. So here it's given pictorially. The equivalent here, you can clearly see that everybody must be clear about it. That electrical circuit we all know is the magnetic circuit. So you can see the source, see the effect. So the magnetic conductor, which is basically called core, that this would be called the magnetic conductor, is represented by the electrical circuit at the resistance. So this relationship. Now, the core reluctance would be given by the length over mu over this. So how does this come along? What things we already know? Let me derive it now here. Flux is ampere turns MMF over reluctance. But flux itself is actually flux density times the core area. Okay. And what is MMF? MMF is basically your Ni, right, over okay, so flux density over here. So but flux density itself, okay, let me expand the left hand side first. So flux equals to this left hand side equals to mu times H, right? Mu is the permeability times H is the magnetic field intensity, and that's equal to mu equals to Ni over Lm, L. Okay. Now if I write flux also equals to Ni over Rc, which is the reluctance of the core, then you can see I can equate both sides. I can clearly see that from this here, I can say that my reluctance for the core is defined by this formula or given by this formula. Now this formula is similar to the resistance of a conductor, which is given by the resistivity multiplied by L over A. Right, so this is the formula for resistance, and you can see that reluctance, reluctance is also given by the similar formula. It's L, presence of L, you see a core here, the core area is actually same as the conductor area, right? And then there is only difference is that here rho appears in the numerator, mu. In other words, for a resistance, if the resistivity is higher, then the resistance will be more. So this is the size of the conductor, right? So however, this, if you look at the reluctance formula, permeability comes in the denominator. So if you have a material with higher permeability, then the reluctance will be lesser, right? So that's basically the relationship between electrical circuit and magnetic circuit. Now, in practice, what will happen is that the path may not be uniform. Like here, it was showing all uniform, the core material, right? The core. But it may so happen that sometimes the core or the path of the magnetic flux is not uniform. You can clearly see that there are cases when we'll learn later that we'll be putting air gap. Now, air is having a different mu compared to the mu of the core. In fact, the mu for the core will be much more than the mu of the air, which is also known as mu naught. So in fact, we also say that all other materials mu or the permeability is given in terms of as a factor called mu r multiplied by mu naught. Mu naught is the permeability of air or free space, and all other materials, normally many magnetic materials have very high mu r, the relative quantity. So whenever we have non-uniform magnetic path, it's same saying that there are non-uniform conductors, right? Suppose a circuit can be made out of different pieces of conductor. One conductor having R1 resistance, the other having R2 resistance. If together they are actually supplied by the same source, we know that the resistance seen by the source Vs is equal to R1 plus R2. Both carry the same current, so both will have some potential drop, voltage drop. So the overall resistance will be sum of the resistance. Now, can you see that something similar would happen here, because the core and the air gap, the same flux lines pass through them. Right? Whenever flux passes through a part of the path, there will be equivalent voltage drop or magnetomotive force drop. So we can clearly see that we can imagine as if the magnetic circuit consists of two sub-circuit resistances. One, which is the reluctance of the core, the other is the reluctance of the gap. Now, the reluctance of the gap will be given by this formula. So you can clearly see that here we are using the mu naught. And if mu is much greater than mu naught, you can see in this equation that Rg, the resistance of the gap, may indeed be greater than the core. Okay. Now, of course, the length of the core is more, but mu will be probably few thousand times. Mu will be few thousand times the value of mu naught. So you can see that normally Rg, if there is air gap in any core, the air gap itself will be the major contributor of the reluctance. Okay, so let me pause here to see whether you guys are with me so far. So I'm trying to show you the equivalent circuit for magnetic circuits like inductor or transformer. So whenever there is a magnetic flux, that circuit can be represented by electrical circuit. So I think we saw the heat flow, right, as electrical equivalent circuit. So this is another application of electrical circuits where we use the magnetic field, or rather the whole magnetic phenomenon in terms of equivalent electrical circuit so that we can use the circuit laws to calculate the various quantities. Now, here, when you have an ideal transformer basically what it does, one coil, there are two coils on the same core. So when it is ideal, the flux will be same both on both primary and secondary. Next question. If the core on the transformer is the sum is in same coolant, then we have to take the coolant properties. What do you mean coolant? Sorry. The coolant will not be magnetic, right? Yeah. Oh, for the air gap, the coolant, yeah, the coolant, if there is coolant, normally those transformers don't use air gap. Normally the air core transformers use air gap. Okay. For those big power transformers, actually, we don't use air gap. Air gaps are normally used in the transformers used in power converters, right? Where, you want a linear property. Whereas because if you introduce air gap, the reluctance will be very high. So you need a large current to produce the flux. Okay, if the flux is large, like in a power transformer, the big 50 hertz transformer, you cannot have that much, you have to have large current to produce the flux. So it will not be efficient. Okay, but power converters are slightly different in that sense. So they normally have air core. Now air core means they're air cooled actually. Sorry, I meant so there's no coolant per se. Not air core, sorry, yeah, it's air cooled. Okay, so ideal transformer will have the same flux, both primary and secondary. And we assume that there are no losses, no leakage, no hysteresis and saturation, because this would cause hysteresis and another type of loss is called eddy current loss, which you learn. And because of that, because the permeability is infinity, if you know, the reluctance is zero. If the reluctance is zero, you won't need any magnetizing current to produce the flux. Right? The flux can be produced without much current, very little or negligible current, magnetizing current is required. So this is the electrical circuit. Because there are two windings, you see the dot convention here. The dot of the transformer. The power flow is always from this direction to this direction, primary to secondary side. So here the current I1 and I2 directions, you can see. So in fact, I1 and I2 this direction should be opposite direction. So they will actually oppose each other. So the net flux or net MMF, if you see here plus and this is plus opposing, will be N1 I1 minus N2 I2. The direction of current here actually is a mistake. So the other direction, because that's the direction of power flow in a normal transformer. So net MMF will be, because of the two windings MMF, so MMF will be the number of turns multiplied by the corresponding current. Okay, so this is an ideal transformer. No losses, just the core reluctance. And core reluctance actually also is zero. Now, if you have a practical transformer, which will have all the losses and all the limited permeability values, so they will have all the things that we ignore. For example, the windings will always have some kind of resistance because they're made out of wires, thin wires, so they'll always have some resistance. And the two windings won't be perfectly coupled. So that's why there would be some leakage. What is leakage? I think I talked about leakage earlier, but leakage is basically when you produce some flux which is local. It doesn't go through the core to the other side, and this is local. So this is the leakage, which is not linking the primary with the secondary. Now these local flux linkage will cause some kind of reduction in the flux, because there's a reduction in the common flux, the mutual flux. So this can be represented by one extra winding, as if there is some extra flux that is local. The local flux can be, now the total flux basically can be thought of having two parts. One, the total flux is local flux or leakage flux, and the common flux or the mutual flux, right? So these two, you can see that they can be thought of as two different coils, two different inductors which produce the flux. Now, this was the ideal one. Now we have to add all the things we neglected. So if we add all the other ones, then they will all appear around it. And this will be the model for the overall practical transformer. Those who did the other module, I think T3506, you would have seen this. Okay, so what are the other terms here? R1, R2 are basically the winding resistance. LL1, LL2 are the leakage inductances. R0 is the core loss. L0 is the magnetizing inductance actually. The current flowing through that is called a magnetizing current. So R0 is actually a resistor representing all the losses in the core. We'll see there are different losses that happen. If you remember, there are two types of normally losses. One is called hysteresis loss. We'll talk about that later. Other type is called eddy current loss. So hysteresis loss are because of the back and forth of whenever the flux is changing in positive and negative, magnetization, demagnetization, then there will be losses every cycle in the, that's called hysteresis loss. Eddy current loss, on the other hand, is whenever the there is a changing magnetic field, it will induce some voltage in the core material, and because core material is also steel, which is a conductor, so there will be some current flowing, in small loops within the core, which are induced by the changing magnetic field. So there will be some undesired or rather unwanted currents flowing within the core itself, and they will be simply causing some heating and some losses, right? These are called eddy current loss. Okay, now what is hysteresis can be understood here, that the magnetic material H, as I said, is the cause, because that's number of turns times current over the length of the core, right? So this is the current. So if you increase the current, normally number of turns and the length of the core is fixed. So if you increase the current, you can increase the magnetic field intensity or H. So as you increase the H here, B will be mu times H normally. So there is a property of the material multiplied by the H. So there will be usually a linear relationship. This is the ideal relationship. But in practice, what happens is that this mu will not be constant. Meaning, if you go on increasing the current, only for a while it will be linear. After that, it will saturate. After that, it will saturate. Right? So this is a saturation effect. The core would be saturated. And this is kind of graph will be different for different material, and this is called VH curve. So what we say, permeability is normally not constant in practice, right? Only for a small range will it be constant, but beyond certain value, mu would be reduced, because you can see the ratio of B and H would be reducing as you increase H, because B would be saturating, not increasing linearly, right? There is one more thing that happens is that when you do AC, that when you magnetize and demagnetize, the BH graph doesn't retreat along the same line. Meaning once you magnetize, increase, then when you remove the current, there is a lag. There's a lag in the sense, if you reduce the current, even though the current has been reduced to zero, the flux would not have come back to zero. The flux has not come back to zero. In fact, you need to have a negative current for the flux to be zero. And if you proceed in the other direction, again, it will be lagging in the other direction. So there's a lag between the current and the the flux in the so whenever you have alternating current, positive, negative, current, then every cycle you complete, magnetization or demagnetization, this some energy would be lost in the process because it's not exactly retreating. There will always be extra effort required to magnetize or demagnetize. So the gap between these two curves actually color BH curve and the process. This is called hysteresis. So you see that in practice, the VH curve will have this problem of saturation and hysteresis, right? So they won't have constant permeability now, but depends upon other things. The permeability mu. Okay, so this is a typical or practical BH curve for a magnetic material. Okay, so next we'll talk about the losses. So what are the losses in a magnetic circuit? So there are two types of losses, core loss and winding loss. Like in the devices, we have two types of losses, right? Switching loss and conduction loss. So the magnetics basically, which is the inductor, will have basically two parts. You can see there is an electrical part which carries the current, and there is a part which hosts or produces the magnetic flux. So the losses in the core are called core loss, and that, like I said, they will be due to hysteresis, and the second one is eddy current. Similarly, the winding which carry the current will have winding loss, which is the ohmic loss or resistive loss or copper loss. There are many names for it, right? You can call it ohmic loss or resistance loss. All due to the resistance of the winding, right? So these are the two types of losses that happen in the magnetics. Now this losses would result in heating, right? The winding as well as the core will get heated because losses are normally converted to heat, like the switching loss and conduction loss in the devices. So practical core material shows a sudden drop in its permeability after what is called a Curie temperature. So what is Curie temperature? You'll see here, this example says that the permeability, if you see, it's temperature dependent, but actually you can see it go on increasing to a certain extent, but after a certain temperature, the permeability suddenly drops from here. So it becomes almost like non-magnetic material. So it loses its magnetic properties and very little magnetic permeability will be there. So even though there is current flowing, the electromagnet will not act as a magnet anymore, right? Beyond certain temperature, that's called Curie temperature. Different material will have different. So here is an example for one material which is commonly used in power electronics called N97 material. That material has a Curie temperature of 230 degrees centigrade. So beyond that temperature, you should not use, right? You should never allow the temperature to go beyond that value. Otherwise, it will lose its magnetic properties. It will behave like a non-magnet. Okay. So that's basically and also the saturation. You can see the B value or the flux density in a core is also temperature dependent. Here are two examples that if you operate at 25-degree room temperature, then the B saturate is around 525 as you see in here, this graph. But if it is the temperature is raised to 100 degrees centigrade, then you can see that it saturates earlier at 400 millitesla. By the way, the unit of B is Tesla. So typically you can see for this core material, it's millitesla. Whereas in the power, we operate at normally more than 1.2, 1.5 Tesla. Whereas in power electronics, for this kind of material, they're normally high frequency material and they don't operate at very high Tesla. Just at the order of 0.5 Tesla. Okay, guys. So I think what I'll do is I'll take a short break of about 10 minutes because I'm just talking and I'm listening. So let's have a short break and then we'll continue after that. Okay. Okay. I just pause the recording. I'll come back after 10. Okay. So I was talking about losses, and the losses can be modeled or can be represented in terms of the various quantities here, and the hysteresis losses, like we saw before, that it's due to the BH loop. So this area here is actually the so if there's a bigger area, then this will be more loss. So you should choose one that doesn't have very fat BH loop, right? But the loss itself is given by, you can see that it's a little bit of typo here. It should be subscript. So it should be pH is equal to KH, which is a constant, multiplied by the frequency, which is the switching frequency for the converter that we use. Then the B max, the maximum value of the flux, because the flux is changing, so this is the B max value in the core, and that to the power alpha. So alpha is given, alpha and KH, the constants are given, then multiplied by the volume of the core, right? What is the overall size of the core? So this is the formula for the hysteresis loss. This is called Steinmetz equation. And you can clearly see that the power here is proportional to the switching frequency, proportional to the volume, overall size of the core, and is also proportional to power of alpha power, B max raised to the power alpha. So that means it is actually proportional to B or even higher order of B, right? It could be, but alpha is more than 1. So we can clearly see hysteresis losses will increase with switching frequency and B max. If you remember the switching losses in power converter, they also depend on the switching frequency, right? A higher switching frequency, there'll be higher loss. So if you operate the converter at higher switching frequency, then the losses in various components are actually higher. But the overall size of the inductor capacitor would be smaller, right? That's why there will always be trade-off between size and basically the switching frequency, the size of the heat sink and size of the magnetic circuit. You cannot operate at a arbitrarily high switching frequency. You have to keep to an optimum value. Now the other losses, which is called the eddy current loss, that is also given by the formula Steinmetz equation here, which says it is Ke. Again here E is the subscript, Ke is that constant of eddy current loss, but here eddy current loss is proportional to the square of the frequency and square of the maximum B. So if you compare these two equations here, the other one, pH hysteresis loss was Kh, some constant, Fs B max to a value alpha, which is not really 2 but less than 2, but greater than 1 normally, and this. So here hysteresis current, hysteresis loss is proportional to frequency, whereas eddy current loss is proportional to square of the frequency. It is more sensitive to increased frequency, right? So how do you know these values? You can get them from data sheet for the material that is used. So eddy current loss is given here pictorially, that these are the small loops within the core. Core is not supposed to carry any current, right? The core's job is to produce the flux or host the flux. But because the flux is changing, it will be creating, inducing voltage, and that voltage will create this. Here is a note. For ferrite material, the eddy current loss are even varying at Vf to the power 4 instead of square. The ferrite material is commonly used in high frequency magnetics like inductors and all, but there Whereas magnetic steel is used for, or silicon steel is used for low frequency in big transformers, right? But ferrite material is used for high frequency. But here it says the eddy current losses still increase at Fs to the power 4 instead of Fs square. Okay, now to summarize these two losses in one page or put them into together, we see that there are two losses inside the core, and then there will be they're all dependent upon these three quantities, right? Fs, Bmax, and of course the size or the volume of the core, right? These three things decide the losses in the core. The losses are also temperature dependent. You can see that there are some material data sheets we have this kind of graphs here. So what this data sheet gives is the left side here, it gives PB, which is the loss per volume kilowatt per meter cube, and on the x-axis is the frequency, switching frequency. So at different frequencies, as you can see, it is the overall losses actually, overall losses, total core loss, not stresses or this. So together, if you see, there will be increasing trend for frequency. As frequency increases, it will be increasing, right? The power of either 1 or 2. So that's why the graph will be like this. But also there is a temperature dependence at the room temperature versus 100 degrees centigrade. The lines are different for the same. And the third thing is at what magnetic flux maximum value are operating. So all these graphs are for different magnetic flux values. So at low magnetic flux, of course, the losses will be low. At high magnetic flux, the losses will be high. So magnetic flux density plus frequency, right? So when both are high, you can see the losses will be higher. And the losses are given as kilowatt per meter cube. So from here, for your operating point, you can actually find out what is the loss per meter cube. So basically the VC is not there. So per volume is there. You can find out what is the overall loss for your operating point, right? Remember, you have to do this if you want to evaluate the efficiency of your converter, right? The right hand side figure again says loss per unit volume, but at different temperature, and the graphs are given for the given frequency and different flux densities. Higher flux density, of course, the losses will be higher, but you see there's a temperature variation. At higher temperatures, the losses seem to be reducing and then again after that it again goes up. So you can see that the losses per volume are actually given like this. So this is unique. I mean, it's not linear relationship or monotonic relationship. It's decreasing as well as it's like the losses will be minimum at this kind of temperature. Losses for volume for different flux densities. So this is given for one particular material which is commonly used in many magnetic design. Okay, so this is all about core losses. The second one is the loss in the winding resistance. Mostly it's resistance loss, right? So resistance loss is basically I square R, and it should be I RMS square R, right? Root mean square R. So that is the loss. Now, in power converters, windings in magnetics often carry high frequency currents in addition to DC current. So if you remember, the inductor current would be always like this, right? If you remember inductor current waveform we draw many times, so there's a DC or average value which you call inductor current, but there is also a ripple. This ripple is quite high frequency, right? It's according to the switching frequency. So when I have a current like this, that's basically what it means, that the windings carry current which has both DC as well as high frequency component. Now the problem with high frequency component current is that high frequency currents do not go through the whole conductor. Suppose you have a conductor like this. As you know, high frequency doesn't go through the whole range of conductor or the whole area of the conductor because of what is called a skin effect. Skin effect is the loss of effective utilization of conductor diameter, because at high frequency, because high frequency will produce magnetic flux inside. There will be induced EMF. So because of that, what will happen is that that current does not flow uniformly. Instead, it actually flows towards the diameter. So if you plot the current density versus the distance from center, DC would be uniform. DC would be covering the whole area. Whereas in AC, the current tends to be avoiding the center. And in fact, higher the frequency, the actual area covered or effective cross-section area actually reduces. So this is called skin effect. That the current tends to flow in the skin of the conductor instead of flowing uniformly throughout the conductor. So effectively the resistance would increase, right? Because the cross-section area actually reduces. So the AC resistance will be higher compared to the DC resistance, right? So in fact, we are operating at few hundred kilohertz. And there is a formula that is given, what is called, the formula is Fs is in hundreds of kilohertz. So how many 100 kilohertz? That you take square root of that. If it is 100, so then you take square root of that, and that's basically the depth. The depth delta here, skin depth. So in all, basically what happens is that the current density decreases exponentially from the surface to the center of the conductor, and there is no current in the center. So the skin depth would actually increase. So the frequency is increased, the skin depth would reduce until it will be very, very small. So effectively the resistance would increase. Now, if that is the case, naturally what you should do, if you have DC current or low frequency current, then it's fine. You can, the current is flowing throughout. But if you are operating in hundreds of kilohertz, the fact that the current only flows, there is certain depth, delta, small delta. So you should try to make the conductor strands. The conductor is not a single strand, right? In fact, it would be built out of multiple strands, with each with a very tiny diameter or tiny radius, so that which is matching with the skin depth, right? Higher the current, higher the frequency of the current, then smaller should be the diameter of the conductor strand. Of course, overall current would require a large area, so you have multiple strands, many tens or hundreds of strands together will carry the current, right? But each strand must be very thin, right? So in fact, that is called lead wire. We'll see that there is a term for it. So that is used for high frequency. So all these power converters, the currents, when the inductor winding and all that, you have to use this kind of wires to wind. You don't use solid conductor because of the high frequency current that flows through them, right? So this is the effect, skin effect. So you have to use these special conductors called lead wires to minimize the loss due to skin effect, right? Because if you just use a thick conductor which is not carrying the, the current is not distributed, basically wastes the conductor area. So you should go for lead wires and choose the strand diameter to be smaller than the skin depth, right? So that at least the strand, whatever area it is mostly the current is spread all through that. Due to proximity, there will be some losses due to the multiple strands. So there will be proximity effect. So we can neglect that proximity effect. Okay, now we understood skin effect. We understood lead wire. That's basically what is done in reducing the effective resistance of the winding. And then once you know the effective resistance, your loss is basically I RMS square times R. So the RMS value of the current is important. Calculate loss, right? So when the inductor we found the average current, ripple current, but we also need to find the RMS current, right? If the ripple is small, then RMS current will be similar to an average value Otherwise, it will be higher. So loss will be higher for the same average current. If it is large, the ripple is large, then IRMS will be higher compared to the average value. Okay, now here is some difference. So how do you choose the material? There are different type of material available for you, and they see each material you have the operating range that is recommended, right, in kilohertz, right? If it is below 100 kilohertz or below 500 kilohertz, then you use different type of material. Each material will have its own mu or permeability. You can see the range of mu's actually are. So these are mu r actually. Mu r. Mu is equal to mu r times mu naught. So mu r is called the relative permeability. So what is it's basically the factor, the multiplying factor with the permeability of free air or free space or air. So that's how you find the mu permeability. So how do you choose? First, if you have certain operating range, you can see here there are three materials in this operating range, N27, 41, 51 here, some example given. And there are some things like for low cost, high power, you use this. Then if you use, there are different applications that are given here. This is the standard material. N87 is the standard material. These are all special material with special applications, but this N87 is a standard material. So how do you choose the material for optimum performance? If you don't know much about the circuit to start with, you can use the standard material. Okay. Because standard material can operate normally over it may not be optimum, but it will be okay for larger temperature and frequency range. Then later on, you can tune up the design. Okay, next we'll talk about the design. How do you design? Now, what is the meaning of design? So normally you have to build an inductor or a transformer, which looks like this. In fact, these are all hand built normally not by researchers. If you want to, or developers or converters, you have to hand build it. Why hand build? You can buy different parts you can order. Then you can choose to put the number of turns as per your requirement, and then you can actually now if you have a winding here, a core, how is the core made? You see here the core normally comes up the material in two split parts, right? For example, if I have two C sections, C cores, I can clamp them together. This is one C, this is another C. I can clamp them together and then then I can put my coil here, one coil, and here one coil. Right? So similarly, this is called C core. There could be E core. Each part comes as an E. So when you put them together, they become E core. Normally it is used for transformer. So you basically put the coil in the center and clamp them together, right? So bring them together, then become E, or they can put the coil in the center part. So there are two types of transformer. You can make it on the sides, or you can make them in the center part. Here is an example where you have put the coils in the center part, right? In the central E. So there are C core and E core. I can say different type of core shapes are available. Now, how to design transformers? Now here it's a transformer does not store energy. What it means is that they don't I think if you know flyback is a coupled inductor, whereas forward we have winding 1 and 2 is a transformer. They don't store energy. So basically they transfer energy from primary to secondary. They don't store energy, right? So they don't operate at a very high flux density. Because when you have no load, whatever is the flux density, with load also it will be like that. Whereas in flyback, if you see the primary is fully charged up and then the energy is transferred to the secondary, right? They don't conduct at the same time. So that's the meaning of You first store energy in the primary and then you turn on the secondary to uh, transfer that energy. Whereas in transformer case, that's, whatever energy comes to the primary, it's passed on to the secondary. It's actually secondary load that decides what is the power drawn from the source. So here, the main purpose is to keep the magnetizing current low, because magnetizing current is in a practical transformer, is the current that is required to build the flux. It is not involved in transfer of power. It's just to build the flux. So this, if it is low, then your transformer will be more efficient. Right? Now, to have low magnetizing current, your RC, the core reluctance, must be small. How do you make the core reluctance small? Air gap normally should be minimum or not there. So you should not have an air gap. It should be closely tight, the core material, no gap. Now, what are the materials you see here? This is called the core. That here you can see, that's also called the core. Now, this part is the plastic part. Actually, that's where you put they are called bobbins. So this is where you wind the coil. The winding is done around it, and that's what it looks like. After you wind it, then you put the core through the bobbin, and that's how you make the final transformer. You tape it, it becomes the transformer. You tap the primary and secondary windings, and that's how you. So you have to choose basically what should be the core size, what should be the bobbin size. Of course, bobbin and core have to match. Then how many number of turns you have to put, what should be the size of the conductor, right? All these things are the design task that you have to do to design a transformer. So how is it done? The transformer, the first starting point is what is called, you use what is called area product method. Area product method here, it starts with what is called the VA or volt ampere rating. Every transformer has volt ampere, right? I think you know probably this from other module. Volt ampere. What is volt ampere? It says what is the operating voltage, maximum volt, and what is the Imax. So from this, or you can see if it is AC, we normally call it the RMS values. So from here, we can actually take the product of this. So this is the power in the level. This is the power handling capacity of the transformer. Now that will decide what is the overall size. Now this, you'll see voltage and current. So to accumulate more voltage, you can see the voltage is proportional to the flux level and the frequency, two things. Flux itself is proportional to the flux density multiplied by the area of the core. So that's what your voltage is proportional to. The current that flows to the winding is proportional to the winding area, because the material that the coil is made, the winding is made of, that will have what is called the highest current density. So that's where the J is the current density. The flux density is the current density, J. Right? The current is proportional to this. So the power, as you can see, will be proportional to the product of this BM, F, J, then AC, AW. Now AC, AW are the core area and the winding area. This together is called the product of areas. Okay, or core, the area product. So core area and the winding area, this together, the product is depends upon the power, right? Voltage times current. So if you know the power rating, divide that by the frequency, the flux density maximum, the J value, and there is one more term here which is called the window utilization factor. Now what is this is, in a window utilization basically means if you have a core, it has a window in which the windings are put. So let me just briefly elaborate here. The windings will be put like this. Now this is the window. This is the window. As you can see, it looks like a window, right? So the windings actually occupy a certain part of the window. It's part of the window because there will be insulation and other things. So each of these will have what is called a window utilization factor. So we know that only 40 to 60% of the window actual space is used by the conductor. The rest is by the insulators and other things and some gaps. So this is window utilization factor. So you can clearly see that the product of these two are decided by what? The size of the core and the size of the window, right? And they are related to the winding area. So what window is basically where the winding will be, core is where the flux will be, right? Window is basically where you can say the current will be, right? The product of these two are related to the power. So starting with the power handling capacity of the transformer, we have to choose the core, and the core catalog actually gives the products. So first you do this, divide this and find the product, and this product will tell you the core size, right? What should be the core, right? So the core that is in the catalog, there will be according to the product. So this product, if you want to know the product, then you can choose a core or that has something close to this or slightly more than this. Okay, so that's basically what you. So you need to know what? You need to know the power handling capacity of the transformer. You need to know the switching frequency. You need to know the maximum flux you want to operate at. KW can take anything between 0.4 to 0.6. And J is the current density of the material we use. Normally we use copper. So we use copper. So current density of copper, if you know, then you can find the SC times AW. Then select the area product and in the market, which is greater than step one. Of course, you should choose something that is greater because that's the minimum you require. And then from the catalog, you choose that. That's how you choose the overall size of the core. You can actually. Next thing we try to find is the number of turns on the primary and the number of turns on the secondary side. And that is given by this formula. It depends on the primary one voltage and primary two voltage of the transformer, right? What voltage you want on the primary and secondary. If you know, based on that, you can use the formula here. All the other things are known. Fs, Bm, but B times M. And this is Fs, Bm. So these quantities, if you know, then you can find the number of turns. And the number of turns have to be in nearest integer, of course, because, right, for example, if you get 14.75, you just take it as 15. So that's how you see how many number of turns you need to find. Then you need to find out what should be the size of the conductor. There are different conductor size that should depend upon what is the area of the conductor, and that depends upon the current on the primary side and the secondary side, right? So from your operation, that all the analysis that we do, then you know what is the maximum current or the RMS value of the current on the primary side and the secondary side. Then you can, based on the current density, you can find what should be the area, and that area will tell you what size or what gauge lead wire you should use, and that's how you choose that. So what did we choose here? We chose the core in step one. What core to use? Core. Step two, basically we calculate step one. Step two, we choose something that is nearest in the catalog, which is bigger than the calculated value. Step three, which decide how many number of turns are necessary for the primary and secondary. And step four, which decide the size of the conductors on the primary and secondary side. So then what we now we can actually do the winding and we can build the transformer. So after step four, the standard practice is to calculate the losses. Then we are supposed to calculate the losses in the transformer and see if the temperature rise is within the design limits. So the power loss we need to calculate. And that loss we know how to calculate from the core loss, winding loss, right? So what is the temperature rise? And then, what is the heat loss? And then if the loss is within that core size, then you go. Otherwise, you go for a higher core size. this is an iterative process. You may not get it right in one go. So because we are not using that information at the time of calculation, you calculate based on other things. So you do a check. This is basically a checking step. If it is not within the limits, then you have to go for the higher one, higher size. Then step 5, we calculate the magnetizing inductance. So what is inductance formula? Inductance L is proportional to what is called the flux linkage over current. Flux linkage is number of turns multiplied by the flux in the divided by the current. And flux itself is divided by B times A or AC over current. And that is V times mu times H, right? Mu H, isn't it? B. So over current. Okay, there's another way you can write it also. We can, instead of flux here, we just write. So there's another way we can write flux. Flux is written as Ni divided by Rc. So that's why it is N square over Rc, the number of turns squared over Rc. And Rc itself is divided by, Lc and mu A, right? Mu Ac. So this is basically the formula for inductance. What is the formula? If you have an coil which has the magnetic core details, know the core material, the core length and core area and number of turns, the inductance of the coil, which is called as the magnetizing inductance, is actually given by this formula: number of turns squared times the core area times the permeability of the core over the length of the core, right? Length of the flux path. Okay, so this flux path you can find from because once you chose the transformer, the core path will be basically this path. So from the data sheet itself, you can find out what is the average length of the flux path. So using that, you can find the magnetizing inductance of the coil. So just get an idea that the inductance of the coil depends upon the square of the number of turns, and the rest of things are actually the core properties, right? The material properties mu, AC the area, cross-section area, and LC the length of the core. Right. So this gives the magnetizing inductance of the core. So you can clearly see that if you want to maximize the magnetizing inductance, then you should increase AC, that is a bigger core. The material, of course, you have chosen already. So you can see bigger AC, smaller LC. This is the magnetizing inductance will be higher. So higher magnetizing inductance means lesser magnetizing current. Okay, so we talked about transformers. Generally, we got an idea that transformer has two windings. So we saw it has to handle certain power. So based on the power, based on the voltage V1, V2, we actually decided what core to use, what size conductors to use, how many turns to wind, and that is how you'll get your transformer, right? So if you have got it right, then you'll get a turns ratio, and then you can put it in your converter, right? So that's one idea about transformer design. Now, inductors are single coils. Of course, there could be coupled inductors also, right? So filter in and coupled inductors, how do you? So the main difference between inductor and transformer is that, so they don't transfer power, right? They just store energy because they're excited one at a time, one coil at a time. So there are no power transfer between winding to winding at the same time. So here the design is slightly different. What happens is that here the current inductor has to operate at a high current, because as the current level increases, it may so happen that the core may get saturated. So you have to make sure that you design in such a way that, so at the operating point, you'll have the data sheet would give what is the saturation flux density, and you make sure that your design is such that the maximum flux density never goes beyond that. Why? Because then once it is saturated, then it doesn't really, its inductance actually effectively drops. So the mu effectively would drop, so the inductance would effectively drop. So we have to design making sure that it doesn't happen that the flux density goes beyond the saturation. And also there is one more thing here. We talked about air gap. In fact, air gap is deliberately added to this kind of inductors to keep them in linear region. Why? Because if you have air gap, your reluctance is effectively increased, and so most of the, basically it's almost like air core. You have, what I mean to say is that you have material, core material, but then there's a gap. So I had given the example that this is the core material, which is mu is higher than mu naught. This is the part which is the gap, very small gap, which is called air gap basically. This gap, the mu is much greater than mu naught. So even though the core length, this is the length of the core, is basically the remaining part, may be greater than Lg, but because mu is much greater than mu naught, so overall R for this whole circuit is dominated by the air gap reluctance. So it behaves more like a air gap reluctance with mu is linear. So in fact, if you do the gap here, most likely the inductor will always operate in the linear region. That means it will behave like air core inductor, which has a linear pH characteristics. Okay. So this is basically how you design the inductor. The steps are given here, but here the starting point to find the area product is, you see here, it's not VA, because in transformer it was VA rating. Here, what are the things? It is the inductance value multiplied by the peak current multiplied by the RMS current. So here the difference, you have to find out what is the inductor value. You have to know what is the required inductor, what is the peak value from the converter simulation or analysis, what is the RMS value. So based on this, you find out what should be the core area, right? That's basically the only difference. Your starting point would be different, L, IP, and IRMS. And then step 2 is to choose that core of slightly higher than step 1. Step 3 is to compute the number of turns. So number of turns there, because it depends upon the voltage. Here it is not voltage, it's L multiplied by the peak current. That decides the, because your peak current and L decides the number of turns that is required for the one inductance. So how does this equation come along? Because again, I told you flux equals to B times A. Flux maximum will be Bm times core area. Flux is your turns divided by N, which is L times IP over N. So that's how you find that N equals to L times IP over Bm times AC, right? So the peak current and the inductance decide what should be the maximum, right? What should be the number of turns in this. Okay, so this AC you would have already found once you know the core. So the core itself is chosen based on the product, but each core, the data sheet will tell you what is AW, what is AC. So from there you can find out what is number of turns. So number of turns, of course, you take it to the nearest integer, and then you to find the current use the current to find what is the area required according to the current density. And then you can calculate the air gap also that is required. How do you find air gap? Air gap is given by mu times n times IP over this. So that means you can see that this is like, when we are operating at the maximum current or the peak current. Maximum current or peak current. So that's the time LG. So you see here, the gap LG is related to RG, right? RG is what? LG over mu naught times AG, right? So N times IP, the total ampere turns divided by RG is equal to flux, which is Vm times AG. So you can see that if I do this division, then you can clearly see, you can find the formula for what is that? NIP mu naught times AG over LG equals to BM times AG. AG will cancel here. LG will become this formula. So these are steps if you are curious. But anyway, as a designer, probably just remember this formula and you find what should be the length of the air gap. Now, how do you introduce the length of the air gap? So typically you have to cut off that kind of gap from the core, like what I was showing just now. Yeah, so you have to cut off this kind of gap. You have to show it off. Or maybe you can buy also certain cores which are readily available with the air gap. Now, there is one more thing that happens when you create an air gap, because in the air gap, the air has low permeability. So what happens is that the flux lines don't go straight. So in fact, the core guides the flux. So when there is no core material, the flux can be swollen or fringing. This is called fringing. So what happens in fringing is that effectively the cross-section area increases and the reluctance of the air gap reduces as the cross-section of the area increases. The reluctance is inversely proportional to the cross-section. And it also causes additional power loss in the core and the winding. Okay, so how do you make sure that the fringing is not much or not a lot? You simply make sure that the length that you come up with, the air gap length, should be less than the square root of the core area. So core area you already know for the core, and LG you calculate like the previous step. Make sure that, just do a check. Do a check that the air gap length is much less than the core area. Now, if that is not satisfied, then you have to go back and you have to do again. So what you do, you choose the next available dimension and repeat the calculations. So this is not a one step or one round. Basically, you have to do multiple rounds, iteration to find the right design. Okay, so that's basically the final step of designing the inductor. So let's just quickly do a recap. So inductor calculation starts with a few things: the value of the inductance. Second thing is the peak current. Peak current, as you know, we already know, right? For the different operation, what is the peak value of the current, right? Inductor current. Third, we know the RMS current. The peak current is related to the maximum flux density that is produced. RMS is related to the loss that the inductor will have, right? So these two values, two forms of the current. That's why we say that we always need to know the peak value, RMS value, average value, right? So this is used in designing the inductor. Okay, so once you know these three, you can find out this product term. Now this product will lead you to in the catalog to one core that has this area. And then once you choose that particular model or size, it will give you the different dimensions, etc. But the next step is to find out what should be the number of turns in the winding of the inductor. So for that, you need inductance and the peak value and the core area which you would have picked from the data sheet. And you then choose the size of the conductor according to the wire, according to the RMS value. Right? You see why peak current is used. Peak current is used in choosing the number of turns. RMS value is used in finding the area of the wire. Then you choose the air gap. Which air gap you have to add air gap for this kind of. So remember, air gap is used in inductors and coupled inductors, right? Energy storage happens and they operate at large flux density. They operate at large flux density, a large current actually. Then you have to be careful that the air gap is there to make the BH graph linear, otherwise there will be saturation immediately. I hope that is clear that inductors operate at high flux density value, whereas transformers don't operate at that high flux density value. Okay, so we basically learned two methods for designing the transformer and the inductor, right? So these two are what we have shown being used in our converters. So after we have done our design and we have made it, we have to do what is called characterization. Characterization is basically finding the RLC value. If you're talking about inductor, why should there be L and R and C? In reality, the winding, anything you make would always have some, because you're operating at high frequency. High frequency inductance and parasitic capacitance would also be there. And the resistance will also be there because it's winding. There's a conductor, and there'll be interturn capacitance also, because it has a multiple turns to build the inductor, and whenever there is insulator between two conductors, right? That's what each wire strand has insulation around it. So we have nearby strands, so there will be alternate conductor, insulator, conductor, insulator. So this is like a series of capacitors, right? So that's why there'll be some capacitance. It's called interturn capacitance. This will not be visible if you're operating on low frequency, but high frequency, they will be important, right? They will be appearing in the circuit. So how do you characterize? How do you find these values? So this is something you do using, there are different ways you can do it. There's something called LCR meter, which measures L, C, and R. So normal multimeter normally measures only R, right? Hardly you get some multimeter which can measure L and C. But that's why you need an LCR meter, which actually does the measurement. Then you have vector frequency response analyzers. So you have VFR analyzers. Frequency analyzers, basically what they do is they vary the input, different frequency sine wave, and they see the output, and they observe the output to input characteristics. So they do basically frequency response of the particular element. So here the inductor also will have RLC. So you can see the inductor transformer, all this will have some RLC. R, L is clear, C is the interturn capacitance. So all this you can actually calculate using these devices. Now for the transformer, the model actually will be the ideal transformer, then the leakage and the resistance, and the magnetizing inductance and the core resistance. But here we would be interested in the interturn capacitance, right? So to find this interturn capacitance, so what you need to do, you have to do that frequency response analyzer, and then you plot. When you do frequency analysis, it provides the gain versus at different frequencies. And if you have RLC circuit like this, then you will see what is called the poles and zeros. So this is the Bode diagram actually. In frequency analysis, you have the Bode diagram, then will give you what is the kernel frequency. And based on these values, you can determine what are the inductance capacitance values. So this is, I'm just giving you an idea if anybody is using this or will be using this. But normally if you do it, you have to do this. So remember, the frequency analyzer plots like this, and based on these values, for example, the first one, low frequency, is due to the value of R and L. So it behaves like RL. The C comes at much later. So the next one here, high frequency one, gives the value of the winding interturn capacitance. The formulas are here. So based on that frequency, the kernel frequency, you can find out what is the CW value, right? So first kernel frequency, these are the kernel frequencies, right? Kernel frequencies. So these kernel frequencies tell you what first kernel frequency gives the value of L0. If you know the value of R, you can find out what is the value of L0 from the frequency. The second frequency gives you the value of CW, the interturn capacitance of the windings. So the short circuit test, open circuit test actually give you different. If you do short circuit test, you will find the leakage inductance. If you do open circuit test, you will find the magnetizing inductance. Right. So this is something we had done before in the module, right? So what is open circuit test? You leave it open and connect the source and the meter like this. Whereas in short circuit test, you short the secondary side like this, and then you connect the meter and the source and the meter like that. And you do the frequency response from there. You identify the kernel frequency and then find out the. Okay, guys. So this is basically all I had to give you some idea about the magnetic circuit and how to design the magnetics for power converters. Okay, now I think this is more or less the material that I had to give. Like I said, this is not examinable, but it's good knowledge to have, which you may use. The concept of magnetic circuit in general. As PE exam, they have magnetic circuits related questions. So you have the basic idea of electrical equivalent, you can actually answer many questions there. And also, anybody is interested in converter, inductor, transformer design, you can use that knowledge for on this. So with that, I have come to the end of the lecture. If anybody has any questions, we can continue. Okay, I'll stop the recording now because officially that's all I had to